In this unit, we will be studying reaction kinetics. As you may be aware, kinetics is the study of movement, such as human kinetics and recreation at Memorial University. Reaction kinetics is the speed or rate at which a chemical reaction occurs. It is also known as the reaction rate. Reaction kinetics can be described in two different ways, qualitatively and quantitatively. Qualitatively means describing it. For instance, how fast or slow the reaction takes place. It's something that you can witness and describe. Bubbles formed, iron rusts, so on and so forth. Reaction kinetics can also be described quantitatively. Quantitatively measures how fast products are formed or how fast reactants are consumed. It can be described mathematically, using the equation rate is equal to the change in quantity over the change in time. This is a formula you're expected to remember. The amount of reactant consumed or product formed over time can be measured by monitoring a change in one of the following: the change in concentration, a change in volume, a change in pressure, a change in mass, a change in pH, a change in conductivity, or a change in color intensity. You should familiarize yourself with the different ways to monitor the change. Let's try this example from a past public. What would one use to measure the rate of this reaction? Pressure, pH, gas volume, or mass? Well, remember from above that pressure is used for gases only. And you'll notice that there are no gases present in this reaction, so we cannot use pressure. pH can only be used for acids or bases, and you'll notice that we have no acids or bases present in this reaction, so we can't use pH. We also cannot use gas volume if there is no gas present, so the only one that we can use here would be a change in mass. And you'll notice that we can look at and weigh how much copper we have before we start the reaction, measure the amount of time for the reaction to occur, and then take that same strip and we can measure the mass of it at the end to see the change in quantity. The next example is not as straightforward. What would one use to measure the rate of this reaction? We have pressure, and there is a gas present. We have pH, and we do have an acid present. Gas volume, again, there is a gas present. And mass. In a multiple choice question, we obviously cannot have multiple answers, so there is one best answer. And whenever we can measure the pH, we'll always go with that answer, because we have a piece of equipment in the lab called a pH meter, which will make it very easy for us to measure the rate. The next example also requires a knowledge of acids and bases. Which reaction would produce the data below? Notice that as time progresses, the pH goes from 1.3 up to 2. Recall from junior high that a pH scale goes from 0 to 14, with neutral being at 7. Acids are between 0 and 7. Bases are between 7 and 14. The closer you get to 0, the more acidic it is, and the closer you get to 14, the more basic it would be. So in our example, seeing as the pH is going from 1 up to 2, it's getting less acidic or more neutral. So we need to figure out which of the following choices, A, B, C, or D, involves it becoming less acidic. Well, in A, you'll notice that these are all gases, and in order for us to have an acid or a base, it must be an aqueous solution. In B, we do have some species that are an aqueous solution, but they are neither an acid nor a base. In C, we have an acid present here as a reactant, and in D, we have an acid present as a product. If we are producing an acid, that means it's going to become more acidic, and if we're using it up as a reactant, it's going to become less acidic. So our answer in this example would be C. We are now going to look at two theories of reaction rates, the kinetic molecular theory and the collision theory. The kinetic molecular theory states that all matter is made up of tiny, microscopic particles that are in constant random motion because they possess kinetic energy. Kinetic energy is also known as the energy of motion and can be denoted as EK or KE. The speed at which the particles of a substance move, as well as the distance between the particles, will determine the physical state of the substance. Both factors increase going from solids to liquids to gases. So the more distance between the particles, the more likely it will be a gas. If the distance between the particles are minimal and they're very compact, it's more likely that it will be a solid. The kinetic molecular theory is supported with two examples. Or there's two everyday examples that proves that matter is made up of particles that are in constant random motion because they possess kinetic energy. The first example would be that of diffusion. If I was to stand at the top of the classroom and I decided to spray perfume, more than likely in a few moments, other students in the class will start to smell the perfume as well. Since I released perfume particles into the air, those perfume particles are in constant random motion and will spread out throughout the classroom. Proof of the kinetic molecular theory. Another example would be that of pressure. For example, a basketball. When you inflate a basketball, the particles inside of the basketball must be in constant random motion and hitting against the inside of the basketball. Otherwise, the basketball would not stay inflated. The collision theory is a very important theory in this unit, and we'll be working with it more in the next lesson. According to the collision theory, in order for a chemical reaction to occur, three conditions must be met. The particles must physically collide with one another. When they physically collide, they must have sufficient energy, which is known as the activation energy, in order to break the bonds. And the particles must collide in the correct orientation in order for new bonds to be formed. In order to increase the reaction rate, you must increase the number of successful collisions between the reactant molecules. And we'll be talking about these factors in the next lesson. As the collision theory states, when particles physically collide, they must collide with enough energy in order to break bonds. This sufficient energy is known as the activation energy and can be denoted as EA. The activation energy is the sufficient energy that is needed for a successful chemical reaction, or it's the minimum amount of kinetic energy required for a reaction to take place. For a reaction to be successful, reactants must meet and exceed this activation energy. If the activation energy is very high, the reaction will have a slow rate. If the activation energy is low, the reaction will have a faster rate. Chemical reactions involve breaking bonds and forming bonds. Breaking a chemical bond requires energy to be put into the bond. This is known as an endothermic process. Forming a chemical bond requires energy to be released when the bond is being formed. This is known as an exothermic process. These two terms are extremely important and will reappear in multiple units in this course. To repeat, an endothermic process is when heat must be put into a reaction in order for it to occur and in order to break the bonds. An everyday example of this would be to melt ice. You would have to put heat into the ice in order for it to melt. An example of an exothermic process where heat must be released would be freezing water. In order to freeze water, heat must be released or it must get colder in order for this to happen. Particle collisions result in the transfer of kinetic energy, which is the energy of movement, to potential energy, which is stored energy, or the potential to move. The kinetic energy of rapidly moving particles becomes transferred to or stored in chemical bonds after collisions. This stored energy is now referred to as potential energy. Think of two cars driving on the highway towards one another. As they are driving towards one another, they possess kinetic energy because they are moving. In a head-on collision, That kinetic energy is transferred to potential energy as the two cars are now stopped. Since there will be a difference in the energy, that energy must be dispersed between the two cars, and therefore you will see damage. As particles continuously collide with sufficient intensity and correct orientation, the potential energy of chemical bonds rapidly increases. When the potential energy reaches an all-time high, some of the bonds are stretched to the maximum that they can be stretched. Since they can't take it any longer, they will break. The breaking of the bonds in the combined particles results in products. New bonds have been formed. Potential energy decreases at this stage. Forming a chemical bond requires energy to be released. A major concept in this unit is drawing potential energy diagrams. Potential energy diagrams are also known as an energy profile diagram, an energy diagram, or a reaction profile. Familiarize yourself with all of these terms, as you may be asked to draw one of them, even though they're all the same, in a test situation, and you don't want to have to get hung up on the terminology. If you know how to draw a potential energy diagram, you know how to draw an energy profile diagram, an energy diagram, or a reaction profile. A potential energy diagram is a diagram that shows the change in potential energy as a reaction progresses. They show the conversion of kinetic energy into potential energy during a reaction. There are two different types of potential energy diagrams, one for an exothermic reaction and one for an endothermic reaction. The only difference between an endothermic potential energy diagram and an exothermic potential energy diagram is the general shape. According to the definition, an exothermic reaction is a reaction where energy is released. Therefore, starting with the reactants, it would make sense that the diagram ends lower to show that energy had been released. An endothermic process is one in which heat is absorbed. So it should make sense that from the reactants, the diagram ends higher to show that energy had been absorbed. No matter if it's an endothermic potential energy diagram or an endothermic potential energy diagram, they both have 5 distinct regions. The first region would be the potential energy of the reactants. So both potential energy diagrams start with a flat region representing the reactants. In a specific example, you would be expected to write those reactants on that line. For instance, A plus B. The next distinct region would be the potential energy gain. So after the reactant, you'll notice that both diagrams proceed upwards. This is the minimum gain in potential energy that results in the stretching of bonds to its breaking point, to the activation energy. So notice that in both diagrams, the energy or potential energy between the reactants and the very top of the diagram is labeled the activation energy. You would be required to label the activation energy in your diagram as well. The next region would be the activated complex, and the activated complex in both would be the very top of the curve. The top of the curve represents the point in which the bonds of the reactant particles are stretched to their breaking point. It is defined as an unstable group of atoms formed at the point where bonds are stretched to its breaking point. It has the highest potential energy. It is neither a reactant nor a product, but a hybrid of the two. It is short-lived and exists only for a fraction of a second. Its particles either form new bonds to give products or will reform old bonds to give the original reactants. You can write it as activated complex, or in your diagram, you can also label it as AC. The fourth distinct region would be the potential energy loss. So after you've reached the activated complex, notice that both diagrams proceed downwards. It's where you stop that determines if it's endothermic or exothermic. Again, if it's exothermic, your potential energy loss will proceed down further than the reactants. If it's an endothermic reaction, your potential energy loss will still stop before the reactants. This is the downhill part of the diagram. It represents the release of energy when new bonds are formed, resulting in product formation. It brings light to the heat of reaction, or delta H. Heat of reaction, or delta H, is the net energy change for a reaction. It is always labeled between the reactants and the products in both diagrams. So the potential energy difference between the reactants and the products is known as the heat of reaction, or delta H. In an endothermic process, delta H will always be positive. In an exothermic reaction, delta H will always have a negative number. The last distinct region in a potential energy diagram is the potential energy of the products, or where the diagram finishes. This is also shown as a flat region to allow room to write in the actual products in an example. For instance, C plus D. The 5 distinct regions of a potential energy diagram are described on the next page. It's very important that you familiarize yourself with these 5 distinct regions so that you are able to reproduce the potential energy diagram. It's also important that you familiarize yourself with some of the key terms, such as the activated complex, as well as the heat of reaction. Lastly, there are several calculations involving potential energy diagrams. For example, you may be asked to calculate the activation energy. In the forward direction, the activation energy is calculated as the difference between the potential energy and the activated complex of the reactants. For the reverse reaction, the activation energy is calculated as the difference between the potential energy of the products and the activated complex. You could also be asked to calculate delta H, or the enthalpy change, or heat of reaction. This is a formula that you are required to remember. Delta H is always equal to the potential energy of the products minus the potential energy of the reactants. If delta H is positive, then it's an endothermic reaction. If delta H is negative, it will be an exothermic reaction. In example number 1, we've been asked to calculate the activation energy of the forward, the activation energy of the reverse, and the delta H for the reaction profile. To find the activation energy in the forward direction, the activation energy for the forward reaction is always the potential energy between the reactants to the activated complex. Notice that the activated complex is at 250 and the reactants start at 50. So EA forward is going to be 250 minus the 50 kilojoules, which gives us an answer of 200 kilojoules. To find the activation energy in the reverse direction, know that a reverse direction means you're working backwards. So the activation energy in the reverse will be between the products and the activated complex. EA reverse, the activated complex still takes place at 250 kilojoules. The products are at 100. So the activation energy in the reverse direction will be 150 kilojoules. Units are very important here. Lastly, we've been asked to calculate delta H. Delta H is always between the products and the reactants, and it's always products minus reactants. The potential energy of the products are at 100, and the potential energy of the reactants are at 50. 100 minus 50 gives us a positive 50 kilojoules for the delta H. Positive meaning this is an endothermic graph. This can be confirmed by the fact that the products are higher than the reactants. We can now do the same thing for example number 2. To find EA forward, it's always between the reactants and the activated complex, or the top of the hill if you want. In this case, the activated complex happens at 100 and the reactants at 40. This gives us an activation energy in the forward direction of 60 kilojoules. To find EA reverse, we always go from products to the activated complex, or top of the hill. The activated complex happens at 100, and our products are at 20 kilojoules. This gives us an EA reverse of 80 kilojoules. Delta H can always be found between reactants and products, and it's always equal to products subtract reactants. Our products happen at 20, our reactants at 40. This gives us a delta H of negative 20 kilojoules. An answer of negative kilojoules lets us know that we have an exothermic reaction. This can also be confirmed by the graph to show that the products are lower than the reactants, telling us that heat has been released. This will bring you to the end of your first lesson. You're strongly encouraged to now try worksheet number 1.